Hi, welcome to the ZP Developer Zone. So we like to do this Developer Zone once a week, and it's really just answering technical questions that have come in during the week. Sometimes these are kind of questions specific to our technology, and sometimes they're just more sort of generic. When I say generic, it's always around the world of electrochemistry and electrochemical sensors, assays, biosensors. I do have some technology in front of me, so I've got a flow cell here. Somebody was asking some questions about a flow cell for a biosensor, so I do have a flow cell here, and I also have a potentiostat, and I'll do some amperometry later on. I just to remember which technique to use. With that said, let me go forward and not sort of tie you up with lots of chat. Links will if you get anything off the web store this month, you can use this discount code and get 10% off. With that said, let me go forward and just say I'm going to talk about flow cells for biosensors. In fact, yeah, I have a flow cell here. This will feature, whoops daisy, shortly in this video. There's an inlet, there's an outlet on here, there's an electrochemical sensor in there as well. It allows us to make good fluidic contact with the biosensor, and it also allows us to make good electrical contact with the sensor as well. I'll talk about biosensors for bioreactors. Plenty of people now interested in putting biosensors inside bioreactors, so I will talk about the technology we have there. I'll also talk about the Djuli account. So in front of me, I've got an app. This app, I can do amperometry with it, open circuit potentiometry, EIS, electrochemical impedance spectroscopy with it. I keep touching over here because we actually drive it through QR codes. Linear sweep voltammetry, cyclic voltammetry, square wave voltammetry. This is a good piece of technology because I will talk about arsenic detection in a bit. And I just want to kind of talk that historically, the reason that some assays haven't left the lab and really gone out there and helped the people it's meant to help is because actually the technology, let's say the potentiostats or the scientific instruments, were kind of too scientific, if I could put it that way, and not user-friendly enough. You'll see me do a couple of demos this evening which will hopefully reduce those barriers. Anyway, the Djuli account, just FYI, if anyone's using one of these instruments, they'll need a Premier account, and the Premier account comes with it free anyway. So I'll touch upon the Djuli account. The word Djuli will become apparent to you as you watch this webinar. I'll talk about arsenic sensors, not so much a review of a paper, but looking at a paper and then talking about how to translate it onto screen printed electrodes such as this. So I'll use this shortly. In fact, yeah, I'll use it shortly to do some work. So arsenic sensors, glucose in sweat. Somebody wants to do some glucose in sweat. They've got a short timeline ahead of them. So we've got glucose sensors, obviously, and we also have sweat, or rather microfluidics that go on the skin. And I think then just a bit on data science. At ZP, we do a lot of wearable biosensors. The data that comes off wearable biosensors can be horrible, but with modern systems like our Djuli system, it's much easier to clean up that data and make it presentable. Just out of interest, if you're interested in workshops with ZP, we do a very kind of hands-on workshop. The next one will be on the 22nd and 23rd of January 2025, and I'll put a link to that. Anytime a link pops up, by the way, they'll also put a link underneath the video as well. So question number one, I'm just doing a sketch out here of a kind of the idea of a sort of a flow cell. And you've got a chamber in that flow cell, and into that chamber you can kind of put a biosensor. I've kind of just sketched it out now, and we've been asked some questions about this. I've had a look at the images. I've kind of sketched up what it looks like, and we have an inlet and we have an outlet, and I just want to kind of touch on this a little bit. It's really important sometimes, kind of, people do go ahead and design new technologies, let's say. You'll notice this is actually a flow cell. I've got the actual flow cell in front of me as well. And inside, this is the actual, let's say, hardware. I have a flow cell that this unclips. I've got a flow cell here. I can just take that off. I could take the sensor out of it. So I just want to kind of say that, if somebody is designing a flow cell, and they're, one way, of making your own flow cell is obviously to sort of take a look at this. We don't necessarily release the designs, but people can purchase it and use it essentially for inspiration. The reason the color keeps going red and blue there is not because we're changing the image. As you can appreciate, when you make a good flow cell, we're literally changing from a red dye to a blue dye just really quickly. And it looks like we're sort of changing the image, but it's actually just when you've got your fluidics set up properly, you can replace the liquid really quickly. So with regards to flow cells for electrochemical biosensors, ZP is very experienced in it. We do contract development, contract manufacturing, including auxiliaries or accessories rather. In fact, I'm just setting this one up now. So I've got my biosensor in there. I can then slide it into here. I can make my electrical contact here, and then I can run that as a flow cell for doing biosensing. So at ZP, yeah, we're very experienced in making flow cells, designing flow cells, making electrical contact, designing and manufacturing sensors for flow cells. I suppose I should just hold this up as a kind of example of the kind of mass production. In fact, I've only picked up half a sheet there of biosensors that we do. We do them on ceramics like PET and also on ceramics as well. Anyway, that said, that's definitely one of our designs at Zimmer Peacock. If you've got any questions about flow cells and biosensors in flow cells, basically don't hesitate to reach out to us. Okay, and you can contact us, and I'll put the link underneath here. Just FYI, we've been working on this for a while. This is the form factor here is about 20 millimeters across, so it's just less than an inch. And this is a biosensor electronic set for actually going into bioreactors. You'll see this app. When I say this app, I've got an app on my phone. This app is downloadable off the Google Play Store and also the Android App Store. It's called Sense It All. I know it's called Sense It All because it says it on the top of the app. And this is actually making Bluetooth connection with many of our electronics. And it allows us to run things like glucose sensors. It allows us to do amperometry experiments. It basically allows us to run our instruments either as potentiostats or as to run them for doing actual analytes. Anyway, the reason I bring it up is because we do get a lot of inquiries around biosensors for bioreactors. And actually we have now started to being able to start releasing this more as a productized format, and it sends all the data to the cloud. And here we're just running a glucose sensor at 5 millimolar, 10 millimolar, 50 millimolar, and 20 millimolar. So at ZP, we are, I suppose, experienced both in fundamental electrochemistry, almost the basic science of it, and then its actual application into many applications. Putting a biosensor in a flow cell is essentially one I wouldn't so much application, but one kind of form factor that you can do, and putting the actual biosensor into the bioreactor itself is another form factor or application that we're also experienced at doing as well. Anyway, but it always has the same core. The same core is it's always electrochemistry, let's say. And I just wanted to kind of touch on this thing that you will see me use the Djuli. If you do get hold of our electronics and you do get hold of a Sense It All potentiostat, this is the Sense It All potentiostat. It's a beautiful thing. If you do get hold of it, just make sure that you do get a Premier account from us. You can always sign up for what's called a Djuli license online anyway. And it's got some limited capability, but when you get hold of the real device, you'll need a Premier account. You'll soon realize you don't have a Premier account, but please go ahead and get one. Now I'm going to jump into something that's a bit more meaty. It's a bit bitty, this is, but somebody was asking me about an arsenic sensor where they kind of oxidize arsenite into arsenate, and I will comment upon that. This is just from memory, but I think it's the arsenite which is actually the most toxic form, and I think the arsenate is less toxic. Now that's my opinion, but I remember first dealing with arsenic, quite a while back. So just out of interest, they sent me the paper. Now it's good to sometimes look at these papers because this paper, there's no criticism of the authors here, but this paper's in 2007. And so some of the kind of comments and assumptions in 2007, I'm commenting upon this paper now in 2025. So you can absolutely understand that we're talking, this work was probably done in 2006, 2005 kind of thing. So we are almost 2 decades later. So it is good to sometimes return to this. Because one of the things they say in the paper is it's hard to detect arsenic because actually, it sort of it runs quite close to copper, and actually that data science and the ability to process data is actually really caught up with this. So that kind of comment, I'm certainly not a criticism of the paper. Don't forget, this is 2 decades later, but actually the data science or the signal extraction has got much better these days, and I'll probably do a demonstration on that in a minute. And I want to give this as a kind of reference that this particular paper, came out in 2014. So to be fair, it's 10 years old. Not a criticism, it's actually 11 years old. Not a criticism of the paper, but what it is when you combine the previous paper on, let's say, arsenic detection with this paper, which I will sort of do a slight combination of that in a minute, the ability to do, I would almost call it baseline extraction or subtraction, and also maybe interference subtraction, means that some of the kind of comments in the first paper where it's like, oh, well, we need this specific sensor because it's very hard to see the signal versus copper. Some of that kind of goes away now because actually we have abilities to do, let's say, better subtraction and better algorithms. So we do have some algorithms in our Sensi-All platform that would actually make it easier to spot arsenic versus the background in copper. And I say here, let me do a demo. So I'll do a quick demonstration in a minute. Unfortunately, I don't have arsenic here, and I also don't have lead or copper here. But I will do a quick demonstration where I'll show you a sort of signal where I've got an interference and I've got then the molecule of interest. It's not so dissimilar to the idea of arsenic in voltammetry being quite close to copper in voltammetry. But I'll show you that we can actually process that data and actually get it down to something that we can actually extract the signal from. So I will, let me just change cameras and do a quick demonstration here. Right, so I've got my phone. It's in amperometry mode at the moment, and I will flick it over to caffeine. Caffeine, that looks good. Yeah, that looks good. All right, so I'm not doing this demonstration for accuracy this evening. I'm doing it for just showing workflow. The reason being is the coffee sample I've made it several days ago, so it's not like the sample's not that stable. Let's say it is, it will be changing with time. So I'll put a sensor in there. I'm just going to get a sample onto that sensor. You saw that I just went from amperometry to caffeine sensing. Just understand this is a very different type of instrument where one can do fundamental science on it and then just use for a QR code which people can generate for themselves, actually turn it into a final instrument as well. So let me just put that sample on and let me do that, which I am doing, and let me just give it a quick name, which I am doing. Caffeine, caffeine 101, so I can find it. Done. Continue. Start. All right, so that is running now, and because I realize that I need to open up a browser, so I'm just going to do that very quickly while that is running there. This is it's a bit hyperbole for me to say it's an amazing system, but it really is an amazing system. When I was doing my PhD, I could never imagine that we would have developed technology like this. The kind of technology stack that we're using here, it wasn't even possible when I was doing my personal PhD. So I'm just logging into something called Djuli. So I've got a result on my phone. So what's holding electrochemistry back most of the time, actually holding electrochemistry in the lab, is actually the fact is, people are not taking the final step and actually turning signal into concentration. But here I have turned signal into concentration. What I want to do is I just want to share this screen with you because it says upload complete on the app. So in fact, what we've done is my phone's in Bluetooth connection with the device with the Sensi-All potentiostat. I ran it. It actually did voltammetry. It sent the data to here. The data was trying to tracking. It went up to the cloud. I just want to kind of share with you why I'm kind of using this as a demonstration. Because I just want to kind of, again, I am not criticizing old papers, especially papers, that are 20 years, from the past. But sometimes then some of the assumptions made in those papers are no longer necessarily the same because the world has changed. And the world has certainly changed in the last 20 years. So in fact, there we go. So I've got my caffeine signal here. This is actually my caffeine peak. This is some interference here. And just look at the way we're able to process this data. I'll just turn that off. So in fact, the idea that, you know, normally you would kind of say, oh, it'd be hard to kind of, you know, draw a baseline in and find the peak height for that. But you can see we just did it automatically because this is one hell of a crazy, or very good. It's got a sort of data pipe built into it, where in fact we've done a baseline. We fitted a baseline, and then we've told it to do peak height versus that baseline. And so in fact, when I look here, you can see it's done a few things. It's forced the baseline to be here. So rather than sort of the baseline being up here, and then we're trying to sort of measure that height. I know you could do this manually, but just in software without any interference from me, we set it up so in fact now it's actually forced the baseline down into here, and we can do that. So understand that if you've got an arsenic and a copper peak next to one another, and the arsenic is kind of being held up or being held higher because of the interference from the copper, it's okay actually. We can have two peaks next to one another like this one, and you can see how by just forcing the baseline here, and we did that by just, if I just go into tools, we just said make a baseline and just fit it to this iterative polynomial, which is a good point actually, because I think I flicked over that a little bit quickly, but I may make the point now actually and go back to it a little bit. Let me just scan back up. Yeah. So what I'm saying is that, in fact, this was the original paper that we read. This paper was 2014. And so rather than that paper having its, let's say, science locked away in it, we've actually implemented it into the database called Djuli, which people can access, and especially useful to access it if you're using our technology stack. But sort of understand that some of the assumptions that were made when that paper was originally written about the detection of, in that particular case, they were kind of saying arsenic's difficult to detect by ASV, anodic stripping voltammetry, because of the interference from copper. Actually, you know, at ZP, we're kind of synergizing all of these things, let's say, including, you know, the baseline correction from this particular paper, which I then just applied to a real world sample. In our particular case, you'll laugh, but the real world sample was actually measuring the caffeine in a coffee sample, but you saw that there were two peaks there, and you know, one of them was just polyphenols and the other one was caffeine, and we were able to actually get the polyphenol contribution out of the signal by using an iterative polynomial baseline. So thank you to that paper, thank you to the original paper. Now I'm going to go back to the main points, but I just want to sometimes say it's worth noting, and just FYI as well, we are actually doing this. The QR code here just says that we can make the Sensi All actually detect lead in water, and we do that commercially as well. And if you're so interested, there are all sorts of videos online. This is Solrun doing a test in our lab, and where she's actually preparing a drinking water sample, and then she'll go on to detect lead in that particular sample. So at ZP, we are definitely using anodic stripping voltammetry in assays to detect heavy metals. Now, at this moment, we haven't done arsenic. I am going to return to the questioner's questions in point, but let me just navigate to possibly here, possibly not. Right, okay. Right, so we are definitely doing that. We are doing it on the Sensi All platform. We are doing it with these electrodes actually, and I'm going to link to a certain type of electrode that this person who wants to do arsenic, I'm going to recommend some electrodes to you because they're carbon. I think they'll also do a good job. I'm also going to recommend that you might have to try platinum, and I'll explain why you might have to try platinum in a minute. But anyway, we're doing our lead detection on this platform. What I love about electrochemistry and what you just saw me do is add a 50 microliter drop. See, that's the beauty of electrochemistry. Also, I mean, I might hold this up actually. Let me just take this sample out. Look at this sample. Look at it. It's brown. That's the beauty of electrochemistry. That's why electrochemistry is a good environmental or good analytical system for environmental samples, by the way, because look at that. It's brown. You could call that like a soil suspension. I mean, it's actually coffee, but you see how dirty it is, let's say. Literally looks dirty, and that's one of the powers of electrochemistry. It's why you should be using that science, especially for real world samples like environmental samples. So we're actually driving that assay using a QR code. The QR code tells our sensor to do lead. In fact, yeah, it tells our sensor to do lead. We run it, we get the data back, we send the data to the cloud called Djuli. You just saw me do that, in fact, and Djuli actually processes that data and turns it into, in the case of lead, back into, I think it's actually ppb, because lead is actually quite, I write ppm here. Am I right? No, it is, maybe it is ppm actually, parts per million. I just want to say one of the things in the paper as well, that I'm going to get back to the science of the paper, but in the paper, they do use a particular potentiostat. Ironically, I've got the potentiostat up on my shelf up here, but they use a particular potentiostat. That is a problem. That is what's holding back so much analytical science, that potentiostats are like this. You can't get them out of the lab. But if you're going to be making sensors for environmental detection, human health, everything's becoming point of care, point of need. So I think what's really holding people back and holding the science in the lab, and they call it the valley of death, and this has been around forever. And so, rather than getting across this valley and getting the sensors into people's, hands who could generally benefit from it, they're held back because actually the instruments that are used to develop it are completely scientific, whereas we actually say, okay, use a small potentiostat like ours, and we are biased, of course, because you can not only do the fundamental science on that potentiostat, but you can then use it to actually launch the new assay as a product, or the new sensor as a product. So at ZP, there's a philosophy at ZP. The philosophy is not just to kind of give, new technology so that people can just carry on doing academic research. No, the philosophy is actually to give technology so that people can do academic research so they can actually get it out of the lab. I mean, this is, when I say this potentiostat, the elegance of its design, the ease of use. This is more like a kind of Apple type product, and it's like that. It's probably the most consumer friendly looking potentiostat that's probably on the market today. So the philosophy is, let's have a scientific instrument that's also something that can actually be used by real people. So it really essentially closes the gap between lab research and actually something that can genuinely be have impact. Everyone's these days getting rated on impact. And impact is, they're kind of doing things like outreach programs and stuff like that. Well, one way of having impact is actually to get the electrochemical assays out of the lab, and it takes a certain type of instrument to do that. Now back to the original paper. Now there's a slight mistake in the original paper, and I'll just bring it up now. Very small, just a typo, not a criticism of the authors, but I did notice it, so I would flag it up. So they're using an enzyme and an enzyme is always a good way of helping with specificity. So they're using an enzyme to oxidize arsenite to arsenate. There seems to be a molybdenum complex in there. This is basically kind of an enzyme cascade where electrons are kind of going from the arsenite. So arsenite's becoming not +3, but becoming +5, and it's the molybdenum that's getting reduced. And then the molybdenum, there's these iron sulfur kind of clusters probably in the enzyme as well, which help to shuttle the electrons down to the electrode. This is not a criticism of the paper, it's just a typo, but in the paper they have this arrow going in the different direction. They have the arrow going from the electrode to the iron sulfur complex here. It's the wrong way around. It's actually going from the iron sulfur complex to the electrode, because they're doing an oxidation at the end, and therefore, well, you can just tell because the cluster goes from reduction to oxidation, so the electrons are going out, whereas in their paper they show it going in, and you can also see it in their paper, in their data as well, that they're showing oxidations, not reductions. So just a quick one, if you're reading this paper, no criticism of them, it's just it's just a typo, and I just want to kind of make sure people appreciate that. In the paper they do they do talk about preparing the electrode. Now they're doing it on a glassy carbon electrode. Yeah, for me, I really find it hard that, if you do research on glassy carbon electrodes, it's kind of like saying, I don't really want to translate this out of the lab and into the real world. I really, and I'm obviously, that kind of, well, it's my mindset, but also, I do, and I could easily be accused of bias, because obviously we're manufacturing screen printed electrodes, but screen printed electrodes exist because Actually, they didn't originate in academia. They actually originated in industry, and they originated for glucose sensing. And I say, of course, because many of you will know that. So they actually were an industry invention that came back into academia. And it's, the reason industry uses them in glucose sensors because they're low cost, easy to produce, and you can eventually, you can give them to consumers or to end users. Well, you can never really give a glassy carbon to anyone. Glassy carbon is a very strictly speaking R&D tool. But anyway, in the paper, they do turn their glassy carbon into a multi-wall carbon nanotube functionalized electrode. I would say that the way they do it in the paper is too harsh to actually do it onto a screen printed electrode. And I would actually say, this has just come to me, that I have many colleagues who, especially 10, 15 years ago, 20 years ago, people were very interested in multi-wall carbon nanotubes. And there's easy ways, and you'll find plenty of papers where actually they're trying to make an electrode essentially functionalized with multi-wall carbon nanotubes, and they're just drop casting. So, I would be taking one of our kind of carbon electrodes. This is the 501, so for example, and just drop casting a little drop, and I'll illustrate this in a minute, onto that. It's not, you don't need to go through this entire process of cleaning, rinsing, piranha solution. I mean, this is, drying. Maybe some drop casting here, and then and then air drying. I would literally just drop cast and air dry. It's important though, because I've got a suspicion that they may actually, in the paper, they're arguing that they're doing the direct electron transfer from the enzyme to the carbon electrode. Now they argue it, but I actually think that the evidence for it is actually a little bit, I wouldn't, weak is not, but it's actually, I'm wondering if that's really the mechanism. And I'll give you an alternative idea on this. So this is their mechanism, that essentially this is a series of electrons are kind of going from arsenite to molybdenum, from molybdenum to these iron sulfur clusters, and then eventually to the electrode. I would actually say it's an oxidase enzyme that they're using in that particular paper. The hint is in the enzyme is oxidase. There's nothing means that, in fact, there's not actually oxygen still in that mechanism. In fact, oxygen is becoming hydrogen peroxide. And if it is, it's important, see, because it means that you can't just, if it is oxygen as the final step, now this is my opinion, right? But if it is oxygen as the final step, you may find it quite hard to just oxidize the generated hydrogen peroxide back to oxygen using a graphite electrode. So that multi-wall carbon nanotube may actually be actually making what's otherwise a carbon electrode more sensitive and able to oxidize hydrogen peroxide back to oxygen. The reason I bring that up is because multi-wall carbon nanotubes may actually have more moieties on them, more oxygen moieties that actually allow them to oxidize hydrogen peroxide. I got a suspicion actually that's what's really happening in this paper. Again, not criticism of the paper, just if somebody makes takes this enzyme, drop casts it straight onto a carbon electrode and says, oh, it's not working. It may be because actually there's an extra step in this which the authors are either not aware of or not thought of, that actually oxygen's in there, and oxygen, when it becomes hydrogen peroxide, it's not that easy to oxidize back to oxygen on a carbon electrode. It's easy enough to sort of, if that does occur, let's say you just use a platinum electrode, but platinum's got its problems because it's actually expensive. But in the paper, it's a bit interesting because they do a galvanostatic deposition of this enzyme onto their carbon electrode. So they do describe it as 10 micrograms for 10 minutes, but it's really strange because I can't see. I feel like they must be denaturing the enzyme in some way, because obviously when you do sort of electrode depositions, you often kind of you may do electropolymerization. You have a monomer, you oxidize it in some way, and the monomers become polymers and encapsulate the enzyme. That would be a kind of classic. But this, they just do it in the presence of the enzyme, so it is strange, but it works. But that is a bit weird. But I would actually say that you probably can just drop cast onto the electrode. So I would sort of be taking, one of our 501 carbon electrodes. If you can get away with carbon, always, anyone out there, if you've got a choice between carbon, platinum and gold, always go for carbon. Why? Carbon is relative to gold. Carbon cost 1/28,000th of gold. Gold is a precious metal. It's traded. It's used in jewelry. It's essentially a currency. You know, there's a lot of competition for gold, but people don't care about carbon so much. So carbon is actually a much more of a commodity chemical or commodity material than gold is. So I think you can actually drop cast both the multi-wall carbon nanotubes and the enzyme onto there. Just a 3 microliter drop onto that would do the trick. And then the nice thing is you can just another nice thing as well is relative to the original paper, it's you basically end up using less materials. I might just do a quick kind of demonstration of. I have to run. When I say I have to run, I've looked at the paper in the original paper. I'm doing this unfortunately in a slightly different way. That in fact in the paper what they do is they kind of have a sample, and then they spike the sample and they spike in and their signal goes up because they're doing an oxidation. The reason I've shown mine as a reduction is because I don't have anything readily available that I can actually oxidize. But I just want to kind of do a demo to kind of demonstrate to you how I think, well, not how I know how they're doing the experiment. So let me just go to here. Let me go into amperometry mode, which I will do by scanning here. I want to just get this QR. There's a QR code up here that I want to get. Open circuit potentiometry, amperometry. All right, cool. Right, so I'm just going to do a quick. What I have with, I'm just gonna call this ferricyanide. Now understand I'm thinking and demoing at the same time, so I might be a little bit clumsy, but right, I'll make that minus 300 millivolts. I'm making this up as I go along, by the way. Unless you've right, so what I'll do is I'm going to take a electrode. I'm going to pretend I'm doing the experiment the way they would do it, and what that means, I'm going to grab myself a pipette, which I have got. I will pick myself up a essentially a blank solution, which I think I'm doing now. I'll just put that onto the electrode. 50 microliters is, that's why I love electrochemistry. It's just a small sample. With, you know, in environmental samples, sometimes, you know, you don't need, you know, there's plenty of sample, but sometimes in the medical world, you know, you need drops of blood, etc. Then people are, you know, you can't be asking for a lot of sample when it's things like blood. With that said, I think I've got that set up correctly. I'm just going to grab something to spike the solution with when I actually do it. I've got that. I will go start. So this is in Bluetooth connection. It tells the potentiostat what to do as long as I set all the numbers right. So off it goes. I'll spike in a bit of ferricyanide. You can see the signal change there because basically I'm putting in a molecule that's this is amperometry, but I'm actually running a reduction amperometry, and it kind of did this big. It's showing us essentially what's called a Cottrell response. Oh, too late. I couldn't add in another bit, but it's analyzing that now, and it will send that data to the cloud. It says upload complete. So I might just quickly go here, go reports, just do a quick refresh here. I realize I'm not sharing my screen, but now I am. Really like this system. Super robust, super slick, and you know, Djuli's been essentially 10 years in production. So I ran my quick amperometry experiment as a reduction, but what they were doing in the paper is they were kind of running their sample, and then they would spike their sample with a known amount of the analytes. They're basically doing a kind of standard addition, and you know, that's understood. Our system will handle that really well. And when you've got that assay kind of running right, you can actually generate your own QR code. So lo and behold, assay not stuck in lab. Assay can go to, you know, Bangladesh, India, wherever, you know, those kind of not pumps as such, but those water sources which might have arsenic in them actually are, and make an impact. And that's really what's important. So I just wanted to kind of do a quick demonstration on that, which I've done. I just want to kind of say I've got a link here, so I'll put this link underneath the video. It will take you to the two electrodes that I think hopefully you can get away with carbon, but you probably have to turn the carbon into a multi-wall carbon nanotube, just drop cast on top of it. Carbon loves carbon, it'll stick to it. Then drop cast the enzyme down onto it. Because when I read that paper, I'm not convinced actually if they are somehow grafting that enzyme onto that surface through galvanostatic amperometry, or then I think it must be denaturing the enzyme in some way. But I would just try a drop casting, to be honest with you. Most a lot of enzymes are quite good at sticking to surfaces, and I suspect that you're trying to do what's called a discrete analysis rather than continuous analysis. Discrete analysis just means I've got a sample, I get the reading, I'm done with it. And if you're having problems, I'd also try out the platinum as well, because there might be oxygen in that enzyme cascade that they weren't necessarily aware of. Question number 5, glucose in sweat. It's probably worth saying that at ZP we do a lot of wearable biosensors, but for people to really engage us on a wearable biosensor with this kind of level where we're actually testing sensors on ourselves and in our facility, you have to be really well funded. But otherwise, you can actually get hold of some of our technology, like a glucose sensor or a sweat patch from us off the web store. So that works well for people who are just trying to get a certain technology readiness level. But I would only say you can only get to the TRL3 using this kind of technology, which is technology readiness level number 3, which is kind of proof of principle in a lab condition. Just to say, you know, this is if you are ending up doing wearables, this is what the data can end up looking like. But through our Djuli system, we're actually able to kind of, you know, filter out this kind of noise and, you know, actually pull out the real signal from the signal plus noise. So the Djuli system does really work well for that. So question number 1, flow cells for bioreactors. At ZP, we're really experienced on biosensors in general, and, you know, I can just reach out into my shelves and pull out, you know, a flow cell. So I would ask people, don't reinvent the wheel. These things kind of exist already. Biosensors for bioreactors, we definitely have now started to bring that to some of our clients. The Djuli, you've seen me use Djuli quite a few times this evening, actually, but if you are using our hardware, you'll actually need a Premier account. The Arsenic sensor, you can definitely do it on a screen printed you can do it on a screen printed electrode. I've read the paper, I've, you know, found a few errors. I'm not criticizing those errors in the paper. It's, you know, it's easy to go through papers and find a few typos here and there. And I think you should try it on the carbon electrode. And if it doesn't quite work, you might have to try the platinum electrode. And even if you try the carbon electrode and you don't find the electron transfer, it may be because oxygen's actually involved in that, and you may have to then functionalize it with multi-wall carbon nanotubes. Glucose in sweat, straightforward. And just to kind of comment on Djuli and wearables, that actually if you are using Djuli in a wearables program, then it's very good at filtering data and getting rid of the high frequency signals, etc., that would otherwise confuse you. If you do have any questions regarding ZP, wearable biosensors, flow cells, bioreactors, arsenic detection, then don't hesitate to reach out to us. Okay, thanks very much.